Hi, getting the stream set up right now. Just chilling out. Hello everyone on Twitch. Hope you can hear me. Give a little bit of time for people to come in. Right. Let me let everyone know internally that this is happening. Okay. Looks like we've got a few folks. Let's tweet this out as well. Getting ready. And I am going to record this locally as well. Okay, let's get started. All right, so hi everyone. My name's Edward, and today I want to do a deep dive on how Torch Dynamo works. So before we actually start looking at any source code, what I want to do is I want to first just talk at a very high level about what Torch Dynamo is and how how architecturally it works. So I've got my handy dandy tablet over here. And I'll just use this to sort of talk about it at a high level. So let me just bring this over. All right. So what exactly are we trying to do when we're talking about Torch Dynamo? So the problem we're trying to solve is that we have a bunch of people who are writing Python code. And in this Python code, there's a bunch of tensor operations like ax plus 2, etc. And what we want to do is we want to somehow extract out a graph of the operations in question so that, for example, I can pass it to a compiler, right? So this is like one of the big problems with eager mode is that eager mode is awesome for debuggability. You can just write, whatever you want, and you can put printf statements wherever you want, and things work just the way you expect them to, right? You just are doing regular old Python operations. And this is really good, except that accelerators keep going faster, and we need a way to actually get out these graphs so that we can compile them together into singular ops so that we can run them. And for the longest time, it was okay to just be an eager mode framework because batch sizes were big and GPUs weren't that fast. So as long as the small amount of code, the Python code on the host could run faster than the actual kernels you were queuing, your eager mode framework would basically be just as fast as a static framework. And so if you looked at something like ResNet, right, that's just not very many operations and they're pretty chunky. And so you don't really have any problems doing it that way. So we don't want to turn PyTorch into a graph mode framework. We want all of your eager mode code to still work, but we still want to somehow capture out bigger spans of operators in question. So the question of the day that we're going to be looking at today is, how does Torch Dynamo actually do this? So here is going to be our strategy. So our strategy for Torch Dynamo is we are going to interpose in at what's called the frame evaluation API in Python. So this was added to Python in order to support JITs. And what it essentially does is, okay, so the way that your CPython interpreter works is that, so you got your Python file, right? And then this gets parsed. and it gets parsed into bytecode. And your bytecode gets run in an interpreter loop inside of CPython to basically actually do all the operations in question. So why do people write bytecodes? They write bytecodes because it is a simpler way of going about writing the interpreter in question. Like the interpreter needs to run pretty fast. It needs to not have that much overhead. So with a bytecode, you can take the entirety of the Surface camera. Thanks, Mark. Yeah, it is a nice camera. 35 millimeter lens. So you've got your parser, right? You squeeze down the entirety of your Surface language, which has got all these random language features, which, by the way, is one of the reasons why writing a direct Python compiler is kind of tricky, because there's a lot of random language features you have to support, and it's all this stuff. So instead, you just run the stock parser, you get bytecode, and then the bytecode is this simplified picture. You never want to code it by hand, but then you can write a loop handling each of the bytecode types, and then once you handle all of them, you've got full coverage for your language. And so CPython just runs this on an interpreter. And so what the frame evaluation API lets you do is, instead of sending this straight to the interpreter, you can pass it to whatever callback you want. Who knows what the callback is? It's entirely up to the user. This callback can, for example, make a modification to the bytecode. So you have the original bytecode and the modified bytecode, and then, for example, pass that to the CPython interpreter. It's also, allowed to, for example, decide to, run some actual, compiled object code, right, to actually execute your code instead of going back to the CPython interpreter. So the plan for Torch Dynamo is we're going to interpose on CPython. We're going to get out the bytecode corresponding to the user Python program that we were given, and then we're just going to do some analysis on it. In particular, what we're going to do is we're going to symbolically evaluate the bytecode, and we'll talk a little bit more about this very shortly. We're going to symbolically evaluate the bytecode, and what that's going to do is it's going to give us all the tensor operations, because we are running the bytecode and we're understanding what the various operations refer to, so we'll be able to pick out when I, for example, do an addition in a PyTorch program. We'll also get some residual Python state. For example, if your code generated some Python object and then returned it, we'll see that, because we're symbolically evaluating the process of creating a dictionary, and then we will in fact reconstruct that inside the Python state via a number of bytecodes, so that if you want to use that dictionary at some later point in time, you actually can. So that's at a very high level what the Torch Dynamo plan is. So this is a live stream, so the point is to get comments and questions from folks in the live stream. So I'm going to pause for a moment while I get set up to look at the source code. But sort of this is I want this to be interactive. Ask me any questions you might have. All right, switching setups. And hopefully this has also given folks enough time to show up and join. Hello, if you're just joining us. There's a question from CF Bulls. How do you deal with CPython changing its bytecode set between versions? The answer is very, very boring, which is that we don't. We have to update Torch Dynamo whenever there's a new CPython version. And in fact, because of this, we don't have a working version of Torch Dynamo for the latest version of Python. Jason tells me that it will be very simple, but we just haven't done it yet. So yeah, that's the deal. Okay, so no, that's not right. Oops, I should have set this up beforehand. Give me a sec. One of the things that is really helpful Oh, haha. CF Bulls is complaining that 311 is going to make the bytecode even weirder. For reference, Carl works on PyPy, which is also it's a just-in-time tracing compiler for Python. And the way they've done it is they write a interpreter for Python in a special restricted version of Python called RPython, and then they trace that. And that's how you actually get a compiler stack out of it. And yeah, so they also have to deal with all of the random stuff that's going on with CPython when they're updating in this case. One of the good things about Torch Dynamo and also PyPy design is we do all of the analysis. I need to capture my display. We do all of the analysis from in Python. So this deep dive would not be like really possible to do live if I actually had to compile everything all at once. This isn't going to work. Let's resize this. Whee! Fancy. This is what I get for doing the entire screen. Okay, here we go. All right, I'm just going to share my terminal. Sorry. Stream problems. As an example of something that's not supported right now, Torch Dynamo doesn't have any support for generators. So if you use a generator in your PyTorch program, it will not actually work. All right, here we go. Yes, Sumith has called in to say for now, which is indeed true. Okay, here we go. Okay, so let's first run a little example. So I'm going to pull this example straight off of the Torch Dynamo GitHub webpage, just so that we can see like what kind of program we're going to be running. So I'm just copying this in. So what's going on here? So we've got our PyTorch program. It's got a bunch of random stuff. Basically, we're torturing Torch Dynamo's ability to trace things that are going on, and we've also got a very simple compiler. This compiler is very dumb. All it does is it prints out the graph that was given to us, and then it just returns a function that will just interpret the graph. So you're not going to get any speed up from doing it this way. And then we turn on Torch Dynamo. So this is the thing that's actually going to turn on the frame evaluator to interpose on the Python bytecode. And then we actually run this on the example. So we can go ahead and run this. And we can see that we get out this graph. And in fact, there are two graphs that we get, because the way this example works is that there's going to be a graph break, because the summation is data dependent. Whether or not the sum of all the elements in this tensor is less than 0 or not depends sort of on whether or not like the data in question is averaging to less than 0 or greater than 0. So we get two graphs, one for the situation where it averages greater than 0, and one for the situation where it's not. And we're going to explain how this all works right now. So that's going to be the plan. Okay, so let's get started. So one very reasonable way to like get started with a program you don't really know is to just go ahead and like start looking at the code in question. So we're going to just go ahead and start looking at the implementation of Torch Dynamo Optimize. So we're in Torch Dynamo, there's going to be some init. We're like, hey, optimize, where does optimize come from? Optimize comes from this file named eval_frame. Let me change directory into Dynamo. Eval_frame. So eval_frame is basically responsible for doing the work of just implementing the actual installation of the frame handler. And there's actually two parts to this code. So there's also a little C stub, which we're going to look at first, which is responsible for actually interacting with the CPython API to install the frame handler. So the way to install a frame handler is, let me do the Python file first. So we said we're going to call optimize. So optimize is some function, the main entry point of Torch Dynamo. And what is it going to do? Well, it is going to so this is actually a function. So convert frame, we're going to get there very shortly. As its name suggests, it's responsible for taking the Python interpreter frame and converting it into the optimized form with an FX graph and all of the bailouts. But we're really going to be interested in this optimize cache errors function. And all this does is it creates this optimized context manager, which inherits from Torch Dynamo context. And what does Torch Dynamo context do? Well, it basically says, hey, give me some callback, and then when you enter me as the context manager, I'm going to set the eval frame to be the callback. And set eval frame is actually implemented from the little bit of C code. So let's hop over to that C code. So set eval frame is going to change the frame callback and return, it returns the old one, but we're not really going to worry about that. And this is the full extent of the API that is provided by Python, which is that there is this field in the interpreter state. So tstate refers to the thread local state for this particular Python thread. Normally there's only one, but if you use the threading module, there's multiple ones. And then you get out the interpreter that's global for the process, and then there is this eval frame, and this by default is just the frame that takes the bytecode and runs this normal CPython bytecode interpreter on it. But for our tastes, we're going to set the eval frame. And how are we going to do this? Well, set eval frame, here we go. Well, there's a few options because, in fact, we take in none and false as valid callbacks. But this guy, enable eval frame, right? It just sets the field on eval frame. So what exactly is this? So like this is really all the integration we need. There's a bunch of stuff that we'll have to look at later when we actually install the code in question. But like, what exactly are we doing here? So what's the frame handler we're going to install? So actually, this doesn't take the callback as the argument, because you don't actually install the callback as the frame. We have a custom eval frame handler, which is going to handle the actual calling of the callback. Okay, so this is a little disorganized, so let's step back for a moment. So where have we been? And hello, everyone who's joined. Please toss all your comments in the chat. I'd love to hear your questions, or just request, hey, go slower, go over that again. Absolutely. So the story so far is we have turned on Torch Dynamo by setting up this context manager. And the context manager is calling into some C code, which is going to stub out the current eval frame handler. And we said in our high-level overview that this eval frame handler is what's going to take a Python frame, a stack frame basically, and actually run the bytecode in question. So we've installed our handler, and our new handler is this custom eval frame function written in C, which is going to do some stuff. And what is it going to do? Well, let's read. So what it's going to do is it's going to first look at our cache and see if there is an entry for it. Because what's going to happen, right, is as we keep running our program with Torch Dynamo, we're going to start compiling various places. And we don't want to keep recompiling everything because the code will just get slower in that case. So we're just going to actually, retain information associated with each of these frames. That's what this get extra thing does. It lets us get out some extra information corresponding to the frame, and we'll save info. Like, for example, this skip code simply says, we tried to compile this, but it didn't work. So don't try to compile it again. Just go ahead and run the default frame execution in this case. And there's also some stuff for getting out the local variables. And then we go ahead and disable our frame handler. And then the next step we do is we say, okay, maybe I've seen this code before. And if I've seen this code before, maybe there is some there is some cached compilation result that I want to reuse immediately. So I look up the cached code and I say, hey, is there already a version? And if there is, and then I want to just go ahead and actually run the cache hit in this case. There's a question from Twitch, which is, what is a PyFrame? Is it just a Python function? So the answer is a PyFrame, specifically a PyFrame object. It is not quite a function because a function is a object that you haven't called yet. So a frame is sort of what happens after you call the function, right? So when I call a function, I need to allocate, a bunch of state on my stack representing like what the intermediate variables are, what the locals are, all of that information. And that all gets balled up into a frame object. So actually when we enter our frame handler, the Python runtime has actually already done all the work setting up the frame at this point. And then we're just going to take a look before we actually execute any of the code in it. And if you want to know more about stacks, you should go watch my PL class lecture about stacks. It's in the context of JavaScript, but many of the same concepts apply. And so, highly recommended if you're like, frames, I'm not sure what that is. I've got a YouTube video about that. Okay, so there's a bunch of stuff going on here, which I'm also going to skip for now. But intuitively, this is how most just-in-time compilers work, right? They say, okay, do I already have a hit for this? If I do, run that code. And if I don't have a hit for this, then I need to do some compilation. And the way we're going to do the compilation is we are going to call our callback. So remember the code that we had earlier. I see your question. Let me get there in a second. So remember that code we had earlier in evalframe.py, right? We called optimize catch errors with this weird convert frame thing, which I told you without proof that this returns a function. So this is our callback. So this is the thing that's going to get called with the current frame object to actually do the compilation question. And the rest of our discussion is going to be in Python. So there's a question, which is, why are we calling into C for this code? And the answer to that is twofold. So one is that you can't actually install a custom frame handler from Python only, right? You actually need to have an honest to goodness C function that's going to do the interpretation. So to interact with that, you need C bindings for it. The second point is this code is hot, right? Whenever I call into frames inside of a Torch Dynamo activated region, I always have to run this code. I'm always running this code, even if there's no compilation that needs to happen, and I'm just looking it up in the cache and then directly jumping to the custom code. So you also want this written in C because this is the thing that you can't amortize over multiple runs, and you want it to work well in that case. Okay. So let's pop back into the Python universe. And let's talk a little bit about convert frame. So we said the callback is convert frame, Technically, it's not convert frame, right? Convert frame returns a function. The frame it returns is this underscore convert frame function. And essentially, what we're going to want to do is we're going to want to, well, what do we do? I forgot what result means. Let me check out what we do with the results. So we're going to call the callback. Call callback. Yeah, call callback. And then if it's null, that means we raised an exception, because that's what null means in CPython binding code. If we didn't get a non-result, we return a new cache entry. So that's the result. So there's some code for actually adding this to the cache that lives on the C side. And otherwise, if we return none, then that just means that we couldn't compile it, and we're going to set this as a skip in this case. Okay, so the result is going to be a cache entry that it represents. This is the code that you should run subject to these conditions, because remember, we are a tracing JIT, and tracing JITs generally specialize on aspects of the input to make them work out. There's some stuff going on here, some counters going on, but you know what we're going to do, right, is we're going to attempt to run inner convert. So that's really the function we care about. So let's look at inner convert. And what is inner convert? Well, it's this function convert frame assert. So let's jump here. And what's going on here? So okay, so there's two parts. So the first part is actually the second part, which is that when we have a compiler function, there's two phases, right? So the first phase is we need to somehow do something to the Python bytecode, which I'm about to describe, to actually get out a graph. In this case, we're using fx graphs as our representation. It's a very simple format. It just, you know, has a bunch of nodes operations one by one by one. And then given this fx graph, we want to pass this to actually some compiler backend to actually run the code in question. And so that's what this compiler fun is about. It basically is going to be what we're going to call on the graph after it gets computed. So we actually just pass it into this instruction translator. There's a question on the Twitch, which is the name Torch Dynamo an allusion to the original Dynamo tracing system? And in fact, I had this question the other day too, because I was reading through the just-in-time literature to prepare for the stream, and yeah, I saw the system Dynamo. So I have no idea. We'll have to ask Jason Ansel about this. Okay. So what exactly is convert frame assert doing? And there's a bunch of stuff here, so let's just get to it, right? So I said we're going to get in a frame, right? The frame is the representation of the Python execution at some point in time. It contains all the locals that we need to access that were passed in as arguments. And in particular, it's got some code, right? So this code is basically the actual bytecode compiled representation of the function in question. There's a great question from Nuckley, which is how deep does Torch Dynamo do the tracing? Does it trace code not really unrelated to PyTorch, such as third-party libraries? And the answer is we do inline, but we have heuristics for basically stopping the tracing. So like there's another module called skip files about things that we know we can soundly skip, just ignore. And also, we also plan to add some more things, because in principle, we could start rabbit holing into arbitrary Python code in a not useful way. And that's not good. But there's one thing I want to say, right? Which is, let's say you're using Torch Dynamo on your PyTorch program, and you're calling some third-party library, but it's like Hugging Face. Right? And Hugging Face has these models, and they have a bunch of operations. What we want to do is we do want to trace into Hugging Face, because we will get more PyTorch operations in that way, and that'll give us more to work with when we're passing it off to our compiler. So, like something to be aware of. Okay, so we've got this bytecode, and there's some stuff like, if we've already seen the code, then don't bother recompiling it. There's a little debugging thing here. It's handy. It basically just says, hey, if you set this debug function, then please don't compile anything except this function. So it's useful if you have like a big program and you only want to execute the compiler on one particular part. And yeah, I said generators are not implemented, so RIP. There's also a cache size limit, because if we've compiled a function too many times, that probably means it's doing something very dynamic. And everyone knows that like the worst, like the death kiss to like just-in-time compiler performance is if you keep recompiling the code over and over again, because compilers are not cheap. And then finally, we get to the actual meat. So I'm going to skip over transform for a moment and skip over these two local calls and get to this. So what we're going to do is we are going to transform the code object with this transform function. And there's some stuff. So I actually don't know why this is here, but I think what's going on is that sometimes Torch Dynamo will get partway through like symbolically evaluating, and they'll be like, "Oh no, I just found out something that I need to like do to like I need to redo the entire trace because I've got this new information and I should have applied this info earlier." So this is a way to like actually do that, but it's not too important for normal execution. And in particular, we've got this transform code object call that's wrapping transform. So where's that defined? Well, it's defined in bytecode transformation. So what we're going to do is we're going to take a quick gander at this bytecode transformation file for a moment. So what exactly are we going to do, right, concretely to actually do this transformation? So Python bytecode is actually just represented as this like string, right? It's just all the bytes representing, you know, like all the bytecode instructions. And that's very irritating. So, sorry, that's great if you're trying to write an efficient interpreter, because you're just going to have a tight loop, right, iterating over, you know, your byte pairs or however long your instructions are. You know, you want a compact thing because that reduces the amount of cache you need for the instruction stream and stuff like that. But for us, we're writing everything in Python, so that's a pain. And so what we're actually going to do is we're going to take this frame and we are going to convert all of the instructions into nice, easy to use Python objects. By the way, this means that our symbolic evaluator is very, very slow, but it doesn't really matter because there aren't that many opcodes we need to symbolically evaluate in a typical PyTorch program. I think Jason told me that let me look up the number. In the benchmark suite we've been doing, the largest models are like only, where is it? Let me find it. Sorry, this is unplanned. Please ask questions. Okay, I can't find it. So essentially, it's like on the order of like 1,000 or something like that. So even though there's like 1,000x slowdown running the symbolic evaluator, it doesn't matter because that's not the sort of topple intent. You're going to spend more time actually compiling the thing. So yeah, so we're going to run the standard Python module dis, which is what actually is the standard disassembler, and then there's a bunch of like sort of extra things we use to swizzle the instructions so that they're a little nicer to work with. And the specifics of the swizzling are not that important, so we're just going to skip over this. But yeah, like for example, bytecodes directly encode like what offset you want to jump to. So that's kind of annoying. So you want to replace that with a pointer to the like location you want to do. There's a question from CF Bowles related. When you start tracing, is that always at the beginning of a function, or can you start tracing a currently running thing? And this is a great question, and the answer is we can only start tracing from the beginning of a function, or really a stack frame. And this mostly has to do with the eval frame API, which like, you know, you install the eval frame handler, but you're already in the midst of like, you know, executing the normal interpreter for, you know, some given function. So it's not like CPython doesn't know how to do this. So you have to wait till you actually enter a new frame. That being said, we are going to have bailouts. We are going to be able to we are going to be able to, what's it called, kick ourselves out of the symbolic evaluator and then run the normal CPython interpreter. So we're going to do the normal JIT stuff that you have to do in the situation. Another question from the chat, how can we hide the compilation overhead from the users? And the answer is right now, Torch Dynamo does not hide this at all. So yes, your code is going to run slow the first time. We have a plan. There's an issue filed for running the compilation separately in another thread so that you don't have to wait. So we'll just run PyTorch, normal eager mode, right? Eager mode is pretty good, and we'll eventually have the compiled version for your code ready, and then we'll call into that. So hopefully, we don't know if this will actually like work in practice or not, but hopefully you won't get that like, time to first graph problem that, Julia people always complain about. Okay, so we've got our cleaned up instructions. They're in a nice object-oriented form. Like if I didn't tell you about this, you probably wouldn't even have noticed. And then we're actually going to run our transformation. So let's go back to convert frame and talk about our transform function. So this is our transformation. So we've got our instructions, and there's a bunch of stuff, but the big kahuna is instruction translator. Okay, instruction translator is our symbolic evaluator. So our plan is we've got this bytecode stream. It's in a form that I can easily, monkey around with in Python, and we are going to build a Python interpreter, right? A bytecode interpreter in Python. This is old hat to CF Bulls because this is what he does all day. We're going to write a Python bytecode interpreter in Python, and we're going to go ahead and symbolically interpret our Python code. And the way this is going to work is most like actual Python computation is going to execute in the normal way. We're just going to go ahead and run it ordinarily. But when we see tensors, we're not going to actually run, we are going to run the tensor computation, but what we are going to do is we're going to record these symbolically. And so each tensor computation corresponds to an operation that is going to get saved to our graph, which is eventually going to get called with this compiler function. So obviously, to run the tracer, we need to know what the instructions we're going to execute are. We need to know what the locals and the globals referred to by this frame are. And there's some other options which are not that important. And so once we are done with the tracer, right, we get some output. This output is just, what is it? The output is the cache entry that we're going to do. I think we return it. Do we return it? We set it to a non-local. Okay. I think output is what we return. Okay, we don't quite return output. We return this guarded codes thing. Okay, I'll talk about that later. And we also get new output instructions. These are just written to the field on the instruction translator. And this represents the new set of bytecode that I'm going to replace my old Python code with. So if you remember when we ran this example, I'm going to run this example again, but this time I'm going to turn on debugging. So when I turn on debugging, it also will tell us, hey, when you gave me this function and we enter this frame, Python gave me this bytecode, right? And this bytecode has a bunch of stuff. It has it does a bunch of things, and I'm going to need to explain what this does very shortly. So this is we're entering the what is a stack machine? How does Python bytecode actually work segment of this stream, and after compiling it, there's some new bytecode, and that's where we're actually going to install into the handler in question. So what actually is going to happen is if all the guards are true for this function, then we can just go ahead and... is that what happens? Yeah, if all the guards are true, then we can just go ahead and run this bytecode, which is going to just go ahead and directly call into our compiled execution. There might be an ordering problem. I'm not sure if the guards run before or after this. We can figure that out shortly. Okay, so the output instructions overwrite the original instructions, and that's what we're going to have later. And there's also some dead code elimination because we don't necessarily do this. So what is instruction translator? And the compiled fun is a native function. That's a good question. So it could be, but like for example, we have plenty of backends which are very dumb. Like we have an eager backend which just then reruns the graph in eager mode. So that would just be a Python callable in that case. Yeah, there is something interesting here which I didn't realize when I was researching this, which is you kind of do want to not go back to the CPython interpreter when you're executing, and I don't know if it's possible to arrange for this to be the case. I think what's going on here is we always go back to the CPython interpreter just to load up the things before we actually make the function call. And then we have to pay the cost of a Python FFI boundary. So maybe it's worthwhile optimizing that. I don't know. But I don't think that's what happens. So we'll bounce to the interpreter and then call the function, which could be native, also couldn't be. Okay, so instruction translator is here. And this is the big kahuna, right? So our plan is to symbolically evaluate Python. And once we do this, we are going to profit, right? Like that's the name of the game. So before I actually dig into this, I want to take a little bit of time to explain what exactly I mean by symbolically evaluate. I also want to talk about what I mean by actually running the code. So to do this, I want to simplify my example a little bit. And I don't care about the compiler, so let's forget about the compiler. We'll just run eager mode. I don't want to run this multiple times. We're just going to run this once. Okay. So we're going ahead and running this. And here's our bytecode, okay? So what I need is I need everyone to understand what this bytecode means, right? Load fast, binary add, return value. What the heck? So let's copy this in a file and talk about it. Okay, so if I just sort of like don't explain anything and just sort of like look at the mnemonics and try to puzzle out what this means. There's some sort of loading going on. There's like some numbers and there's some like number here. I don't know what that means. We like load a 0, which is A. We load a 1, which is B. They load to somewhere. Where do they load? And then there's some binary add thing, which makes sense, right? Because remember our original code was def A, B, return A plus B. And then we would like return value, so that kind of looks like the return. So even if you know nothing about Python or about bytecodes or anything like that, we can kind of see that, like operationally, imperatively, what we're doing is we're loading some stuff. In particular, we're loading the arguments. So every argument to the function needs to get loaded somewhere, and we'll talk about where that somewhere is. And then I want a binary add. Notice that binary add doesn't say anything about what it's adding. So probably related to the loading. And then we return, right? So this like kind of just makes sense. It is what this function is doing at some very low level operational sense. Okay, so to understand how binary add knows what its inputs are and what's going on with load fast, we need to know that Python bytecode is a stack machine. So what do I mean by a stack machine? So when I'm evaluating code in the Python interpreter, what I do is I maintain a stack. So we'll just represent the stack as a list. And this stack represents sort of the objects that I'm working with at any given point in time. So if I want to call a function, say I want to call binary add, what binary add is going to do is it's going to look at the top 2 elements of the stack, pop them off of the stack, and then push on the stack the result of the element in question. So this is a very popular design for virtual machines. JVM is also a stack machine. The other option for writing VMs is to basically write a register machine where you explicitly have registers which you can put intermediate values in, and then when you write instructions, you say which registers you want to pull them from. So register machines are like a little easier to write. Well, I don't want to like talk in general terms here, but register machines are a little easier to write fast interpreters for, but stack machines are very, very simple and don't require register allocation. And in fact, another way to think of a stack machine is it's actually just postfix notation. So like if I write this, load fast, load, binary add, return, right? What's going on is these loads represent the arguments to this postfix expression, which then would be parenthesized like this, and then this entire thing gets returned. So let's go ahead and step through this. So I first load fast, so I'm loading whatever the contents of the first argument, the first positional argument is. That's going to be A. I don't know what it is, but I'm going to push that onto my stack. Then I'm going to load B onto my stack, pushing that on top. And then binary add, what did I say that does? It pops the two elements off of the stack and then pushes the result of having added them. So I'm just going to say add. And then returning will just return the top element of the stack. And then there's like a bunch of opcodes that do things like swap the two arguments on the stack. There's ways to like move things around, push constants on, all that stuff. And we are going to have to write a rule for every single one of these when we're writing our symbolic interpreter, right? So like if a non-symbolic interpreter might have loaded 3, 4, and then 5, and then pop them and push 9 on them, but what we're going to do instead is we're not going to actually concretize all the values. We're going to symbolically represent them so that we can extract out a graph that says what we're going to do in this case. Okay, so that's it for what is a bytecode. So let's jump back to our code, to our instruction translator. So now that I've told you that we need to implement load fast, we can just go ahead and look at the load fast implementation. So the convention here is that every method on instruction translator corresponds to a instruction. So if I want to find load fast, I just search for load fast here, and here I've got it. So and every instruction handler takes in the instruction, which contains any extra information about what's going on. So the load fast instruction also has to encode a single number. That's the argval that says what argument value I'm loading in this case. So that was 0 and 1 in the example we were just talking about. Okay, there's some stuff going on here, but the important thing is this call, right? So self.push. Well, there's a stack machine, right? So pushing is what actually involves like there's a stack, right? So if I call a method called push, I don't even need to show you this method, but I'm going to show you it anyway, right? It just appends the value to the stack. And we're going to get this out of this variable called symbolic locals. And all that basically is when we are setting up the function, and I didn't look at the constructor because it's kind of complicated and I don't want to look at it right now, but when we were setting things up, right, we got in from the frame, hey, here are all of the locals corresponding to the invocation of the frame in question, right? So all we have to do was, let's actually look at what sets up symbolic locals. Where is it? Is it this one? No, this is prune dead locals. This is replace all. This is load fast, delete fast, copy graph state. I don't care about that. Init. Oh, this is very boring though. So I apparently got in a dictionary of all the symbolic locals, and I just do this directly. Is that really all that happens? No. So actually what happens is I set them up here. So remember that frame object, right? And it had a bunch of random crap in it, like the F code and F locals and F globals. Well, F locals is precisely the data structure that represents all the locals that are live on entry to the frame in question. Well, maybe not live, but are actually used by the frame in the bytecode. And so what do? Well, there's this variable builder thing. And I'll talk about what this is in a little bit. But, we just pull out that local and we say, okay, it's the symbolic variable representing the entry in question. And we're going to just stick this in a dictionary for each of the locals here. Is that true? Oh, there's this vars thing as well. What does this do? I didn't look at this. Cell and free vars. What does this do? Okay, there's some handling for like handling free variables for lambdas, which I'm not going to care about. Okay. So there's a question, which is, do symbolic variables also have real values attached? And the answer is yes, right? So we're not, because we're going to be a tracing JIT, right? So whenever we like do something like control flow and we need to actually look under the covers and see what the actual honest to goodness value was, we have to actually have the real value to figure it out. And so what's going to happen is when this occurs, we're also going to record, hey, this is something that we need to either add a guard for, and we can't always add guards because in general, discursion about how tracing JITs normally work. So normally, like if you're looking at a JavaScript VM, the way the tracing JIT works is that we're going to trace through the code, giving some straight line code, and intermittently inside of this code, there will be conditions. These conditions correspond to places where execution would have branched in the original program. And so we basically need to assert that the condition is actually true in that case. And if the condition is not true, we're going to branch. We need to get off the optimized path and into the de-optimized case that can run afterwards. So this works great for traditional tracing compilers, but most deep learning compilers don't actually know how to do bailouts. Like it's like you're writing this CUDA kernel, right? And then like in the middle of the CUDA kernel, you're like, this value is not 0. And in the original code, I like looked at the value and decided to go call some other CUDA kernel. What the heck do I do, right? So I can't actually put bailouts everywhere inside of my function. So what I have to do instead is I have to either be able to move the guard all the way to the beginning of this function. And this is an optimization that you want to do in traditional tracing JITs anyway, because like, not necessarily moving it all the way to the beginning, but like you want to like common up guards and like, get rid of ones that guards that are weaker than other guards. You don't want to like keep testing the same thing over and over again, but we have to do it in the deep learning context. And so if we can't actually do this hoisting because it's like too complicated, it's some like really complicated intermediate expression that we don't know anything about, we're going to graph break. And this is like the secret weapon of Dynamo, which is that we are always allowed to graph break and go do something else, go de-optimize and go to the standard case. And the compiler isn't going to see it. So I guess this is kind of like the bailout code in a normal tracing system, but the compilers never see it. They just see a graph that is smaller than what they saw before. So we can't give the off ramps to the compiler itself. Okay, so let's go back to load fast. Actually, we're mostly done. So there's some extra goop, and I have no idea what this does, so I'm just not going to talk about it. But like you can see that we take the the variable that was stored in symbolic locals at construction, and we push it onto the stack. And let's look at add binop add, binary add, and this just says, hey, I'm a stack operator calling operator.add. So because there's a lot of these and they all happen very regularly. And so what exactly does this do? Okay, there's some stuff going on. But the important line here is, hey, we need to pop however many arguments this function takes. And we're a bit naughty here. We're figuring it out just by taking out the looking at the parameters from the inspection of the function question. So add has 2 arguments. So we pop that many things, and then there's this thing we do to like call the function, and we'll talk about this in a moment, and then we push that result onto the stack. But this you can think of as the thing that will do the symbolic evaluation if necessary. We'll do a concrete evaluation otherwise and give you either a symbolic or concrete value back, and then we're going to just push that back on the stack. Right? So we got everything. We got all our stuff. And like this works exactly the way we expected it to, based on our description of how stack machines work. And then, what does return value do? Well, this just actually says, all right, time to pack it up. Nothing else to do. And we'll actually compile the output subgraph at this point in time. What is going on here? Self.output, I guess, is the representation of what we wanted to do afterwards. And funny comment from Sipol, that's not naughty, that's great use of reflection. Oh yeah, absolutely. So we compile, so we're going to run the compiler in this case, and then we are going to there's just a little bit of extra stuff. So remember, we're responsible for creating a residual bytecode, which is, you know, what you're going to run instead. And so we do need to like actually return in this case. Okay, there's a question from BD Hirsch. Do we always want a graph break since it can prevent fusions? Is there some reasonable heuristic for when to or not to graph break? So the answer, let me think. So the answer is you actually don't have a choice. If you are not able to hoist a guard all the way to the top of your function, then you have to graph break, because you just do not know when you initially started executing your code whether or not this condition was going to go true or false. So a pretty common situation is, for example, you run non-zero and then you test what the size of the output is, right? So this isn't going to work because well, like, you have no idea, right? You have to actually do the compute to get there. If you can hoist, then there is a policy decision you can make, right? So you can either choose to put in the guard, risking that your trace is over specialized and that you'll have to recompile it again later, or you can still do the graph break and then you have a more generic trace which doesn't have that guard. And like, yeah, the heuristic, the very simple one is basically, assume that you want to trace as much as possible and then de-optimize when you notice that things are not going well. Or you can do it the other way as well. There's a question from CF Bowles, which is, I remember you saying earlier that you treat Python values and tensor values differently while tracing. How does this exactly work? And that's a great question. And to answer this question, we need to look at variables. So we need to look at what the actual symbolic representation of things are. So, boop, 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 boop. Okay, let's just go straight there. So this is all in the aptly named variables, and there's a bunch of stuff which I don't care about yet, and the class that I do care about, oh, it's not variable tracker. Is it variable tracker? Oh, I don't think it's variable tracker. I guess it is variable tracker. Okay. This part was a little hazy in my head, so I need to check my notes. Okay, there's variable builder and there's variable tracker. Let's talk about variable tracker. So variable tracker morally represents our symbolic values in question. And so this forms a class hierarchy. So we're going to actually go ahead and implement subclasses for everything we support. By the way, so Torch Dynamo, so whenever you're writing a JIT for like a complicated language like Python, you have a decision to make, right? Which is like, how are you actually going to model all of the rando API calls that can be made in this language? And especially with CPython, right? Like most of the stuff is not in the bytecode. They're like just these random like C API calls that like exist in CPython or like exist in PyTorch, and there's just no reasonable way to get information about them. So the approach Torch Dynamo took, and which I think is like the only viable, well, no, it is possible. And like actually PyPy is like doing some stuff with C extensions. I don't remember what the state of this is. So you can do it the other way, but Torch Dynamo takes the like sort of very incrementalist, will be buggy to start with, but like you can fix the bugs, which is we're just going to like code in enough smarts in our symbolic evaluator to know exactly what all these C API calls are supposed to do. And that's just the idea. So okay, I want to look at let's look at dictionaries. I like dictionaries. So So here is an example of a variable, and it's a lot more instructive to look at the example. So constant variable is what shows up when you are manipulating dictionaries inside of a Torch Dynamo traced region. So let's actually take a look at what this looks like on our example. So let's allocate a dictionary, and then let's set some stuff on it, and then we're going to return the dictionary. I hope this works. Yeah, this worked. Okay. So we need to put on our Stack Machine hats and understand what the bytecode is going on here. So what the heck's going on here? So what we're saying is, okay, build a map. So we're going to create an empty dictionary. Store fast. Store the map to the D local, I guess. I'm trying to remember what exactly this does. I actually have no idea what these opcodes do. maybe some of those Twitch streamers can do that. But intuitively, what's going on is I'm going to create a new dictionary, and then I need to load up my constants, because what I said I was going to do is I'm going to add 1 and 2, and I was also actually, let me make this a little less confusing. So let's make these big numbers: 55, 67, 32. Oh, I see. Okay, here we go. Actually, I have no idea. So what I see. Python already constant folded this for me. Okay, I don't want you to constant fold this for me. Let's fix this. Here we go. Okay, so we create a map. We need to load up our B argument. We also push a constant onto the stack. That's the 67. So if you remember, we're adding 67 with B. So we do this. We do a binary add to add them together, and then we need to put in another constant that says what the index is going to be. We also are going to write it to this dictionary, and then we store. So when I do a dictionary assignment, that's got its own bytecode, and this is going to be important because we're going to fix a bug related to this bytecode very shortly. And so we've got our dictionary, we've got the key, and we've got the value that we're going to store in. That was the result of the binary add. And then finally, we're going to put this on the stack, I guess, and then return it. Okay? So that's what this code looks like. So what happens when Torch Dynamo runs? Well, it got simpler. In fact, there were no tensor computations in this code at all, but somehow the code got simpler anyway. And that's because we are a specializing tracing JIT, and we are going to specialize on the values of all the Python code in question. So what's going on here is it's saying, hey, I happen to know that you called B with 32 at this point in time. And so when I did some evaluation, I figured out that the result of adding 67 and 32 is 99. So I'm just going to load that constant straight up here, stick this inside the dictionary with the result, which is at the key 55, and just return that directly. So this is actually pretty different than, for example, when I was talking to Zachary about this, he was like, yeah, this was pretty surprising to him. And why was it surprising to him? So normally what you would do is you would save all of the bytecodes that you sort of weren't normally weren't handled. Save all the bytecodes that didn't involve any tensor operations, and then just put those in the residual stream. But actually what's going on is we're actually, honest to goodness, symbolically evaluating everything. So at the end of symbolically evaluating this function, where we know that B is 32 because we're specializing on this, we are actually we actually know that at the end, D is supposed to be a dictionary that maps 55 to 99. And so instead, we just write out a bunch of bytecodes to actually reconstruct this state. And we'll look at the code that is actually responsible for doing that very shortly. And we see that this results in a new guard, which is that B has to be 32 the next time around. Otherwise, this isn't allowed. There is a chat message. Bytecodes are just a parallel construction scheme created by big ASM to scam us into thinking Python don't run magic compilers. Well, I mean, Python is very hard to compile properly. So people have worked a lot. I absolutely want to acknowledge their works. What's kind of going on here with Torch Dynamo is we're taking tons of shortcuts because deep learning is weird, and the name of the game is different in this situation. Okay, so let's take a look at what's going on with cons proxy. Okay, so how do I want to do this? Well, let's just talk about what this representation looks like, right? So to create a constant variable, I need to actually, have an items. There is a question which is, what is the dict value is the result of a tensor operation? That's a great question. Let's just run it. I have no idea. So we'll just do plus A. Yeah, plus A, plus B. Sure. Yeah, so what happened is we go ahead and run the tensor computation. That gives us a graph output, and then we go ahead and store that in the dict. And I guess I should have done something more clever like this. And we can still see that the key gets specialized. Actually, we don't even need to. Oh, this is boring. Boring. Let's actually do a graph. It still gets specialized. The key computation, for example. Okay, but we have to store items, right? And so there's a bunch of operations that are defined on this thing. So remember there was this call function method thing that I said I don't know what it is. Well, so whenever we do operations on these symbolic variables, we call methods on them or we call functions on them, well, that's just going to go to the call method object here, which is actually going to attempt to do something with it, right? So for example, if I set item, which is I think what I did in this particular case, there's a bunch of checks that I need to do. So what's going on? So I need to make sure that so I need to make sure that the key is a Python constant, which makes sense. So let's go ahead and break this for a moment. So what if I take a item and use that as the key, right? So we can't really specialize in this case. And wow, incredible. Oh no, it's not supposed to do this. Ha ha ha, okay, bug report. Okay, so what appears to have happened is that Torch Dynamo specialized the, oh gosh. Oh no. Torch Dynamo specialized the thing that it actually saw and built it into the map. Okay, we'll go ahead and report this bug later after the stream. But what is going on is you can see that there's actually no compiled function here because there was what's going on? I have no idea what's going on here. So let's just forget this happened at all. I have no idea. Sorry, this code is also new to me too. Okay, but so what we're going to do is we're going to say, okay, well the key has to be a Python constant, and this dictionary has to be what's called a mutable local. And intuitively, what this means is that this dictionary better have been allocated locally, because if it's some global variable, then that's kind of very strange, right? Because I need to actually make sure that I can't do this trick where I just have this symbolic value representing the dictionary, and then when I'm done, I like just go ahead and create it and return it, right? If I'm editing a global, I need to actually emit the honest to goodness set item calls on the global in question. So if all of these things are true, then I can just go ahead and create a new value, right? So I'm going to take what is val anyway? So val is self.items, right? So it's the representation of what the state of the dictionary was. I'm going to make a copy because we are nice and well-educated, purely functional programmers, and we love immutable data structures. So I'm not going to mutate the thing in place. I'm going to create a new structure, new val. I'm going to go ahead and add that new mapping to the dictionary. So I'm just doing the good old-fashioned dictionary interpretation, and then I need to actually go ahead and like find all of the like old references to this object and replace it with a new representation in this case. What is TX? I forgot what TX is. I think TX is the instruction translator, but I don't remember. Let's see. A val frame. Def replace all. It's not, sorry, a symbolic convert, def replace all. Yeah. So this does something. I actually have no idea what this does, but there's some sort of like mutation tracking thing going on for this situation. Of course, doing something like just get item is a lot simpler, right? We just go ahead and return it with some wibbling of some of the options on the symbolic variable in question. Okay, so you might be wondering, okay, that's cool, Ed, but like, what about tensors, right? Aren't tensors the most important thing? So let's just find that. So variables tensor.py. So we've got a tensor variable, and let's just look at a method call, and I mean, you can see there's a bunch of method calls, and but in general, what we do is when you call a method on a tensor, we are going to create a new tensor variable representing the output of the thing in question. And then on our recorded graph, we're just going to record. And so this create proxy thing is the FX IR API. We're going to say, okay, record a method call on this function with all the arguments that we observed in question, right? And it's just like what you expect. There's one more thing, which is like there's also this business with variable builder. Is that here? Which we noticed earlier, and that basically is just when you like write something like torch.add. Let's go back to example again. So this time I'm not going to use the built-in add op. I'm going to use torch.add, right? When you do this, and you look at the bytecode for this, what's actually happening is the like torch.add gets decomposed, right? We first load torch, and then we get the method add from torch, and then we add it. So variable builder is just like sort of taking this and then saying, okay, well, I don't want to actually do all this stuff. At the end, I have a torch.add reference in this case. Okay, details. All right, so I promised everyone that I was going to try to fix a bug. I also want to talk about bailouts. Okay, so let's talk about bailouts and then let's fix the bug. Okay, so up until now, I've been looking at very well-behaved, easy to symbolically evaluate things. Namely, I've been just looking at like good old-fashioned do some compute, right? We looked like load fast, we looked at do a bin op, we looked at like set attrib, and these just do something. They always do the same thing. There's no divergence depending on what values are, right? But there's also like not so nice instructions. Sorry, I need to go back to the example, right? So for example, not so nice instruction is something like if a dot sum is 0, return b a plus 2 1, else return a plus 2, right? So when I run this, something very oh, this is too clever. Wait, is it? What did I do wrong? So what's going on is it's specializing. Oh, maybe I need to no, this should specialize away too. Yeah, this specializes away. I need to induce a graph break. How am I going to induce a graph break? Okay, let's do this. Yeah, that's going to be annoying, so I don't want to do that. Let's do this. I think this will work. This didn't do a graph update. It's too smart. It's too smart. Okay, let's run it multiple times. Fine. No, but that's not okay, because what's going to happen is it is going to, yeah, it just gave me the, oh yeah, here we go. Oh, you know what? I just got deceived. Oh, no, it was fine. I don't need to call it multiple times. Sorry, this graph only has one thing, but this graph has stuff. Okay, so running short on time. So let's talk about this. So I got deceived because actually there were 2 bytecode things going on, and I only looked at the last one. And the last one, of course, doesn't have a continuation, but this one does have a continuation. So let's hop to it. So the code I wrote was basically run a.sum and then check if it's 0. And so we've got our bytecode for the situation, and we can see that it looks kind of reasonable, right? So we call sum on a, and then we check if it's equal to 0, and then we've got this pop jump if false, right? So that's control flow. It's going to jump to 20 where we add a plus 2 if it's false, and it's going to fall through if the comparison result was true. So when we want to compile this, as I said previously, we have no way of like actually figuring out that, you know, it's going to be one way or another when we enter, because that would be like some very complicated guard that it would actually have to do tensor computations. So we're going to graph break. So this is what a graph break looks like in that situation. So what's going on? So we go ahead and we're going to load our compiled function and run it. And just take a quick look at the fx function here, right? This fx function does, it's got an a argument, it sums it, it tests if it's equal to 0, and then it just returns at that point. It returns the result of the equality test here. So once we run this function, we will have the result of the equality test. And then we just go ahead and do the control flow that was in the original program. And then there's these resume continuations, which basically say how to actually go about executing the rest of the function after you've done this. And then what we see here is that the resume continuations also can be traced by Torch Dynamo. So we're able to capture this little tiny useless graph a plus 2 in this particular case because it was greater than 0, less than 0, something like that. Okay, so when we do conditions on things that are not statically known, and that includes like data-dependent computation results, that's the situation a graph break happens. So let's take a look at how this actually happens. So pop jump if false. So this is a opcode, and it calls this generic jump function. So what does generic jump do? Okay, so there's a bunch of stuff. So we've got our instruction, and we've got this variable tracker, and we're going to there are some guards associated with this value. So we're now going to update the set of guards associated with this function with whatever the guards associated with that value were. And then if this value is a constant, it's a Python constant, so that is to say we know exactly what it is. It isn't one of the symbolic variables we're tracing through our code. All we need to do is just actually like poke at it, see if it's true or not, and then if it is, we can just go ahead and do the jump in our interpreter. So control flow that depends on stuff that we guarded over, stuff that is statically known to be some particular value, we can just trace through that by just doing the jump as was requested. But if we get a tensor variable, some variable that was derived from tensor computation, we don't want to do that. And so what we're going to do instead is we're going to do this resume continuation stuff, right? So we're going to go ahead and immediately compile the subgraph at this point in time, right? So we're doing this condition test on this value. So we go ahead and we push this value onto the stack, and then we compile it, having that be the sort of result. That's what's going to be. This is going to be one of the locals that is going to be expected to be materialized by the compiled subgraph when we are done, and we pop it afterwards. And then we just need to take. We need to create our continuation functions for each of the jump branches, and we just add instructions for handling that case, and sort of we're done at this point. We don't trace anymore, right? So there's a choice, right? Either we know it and then we just do the jump directly, or we don't know it and we do a graph break by immediately compiling the graph and then setting up continuations, which we can actually just start compiling at some later point in time. Okay, so it's 4:28, so I am now going to do what I promised, which is I am going to actually do the bug that I wanted to do. So let's take a look. So the bug report, which you can find on my Twitter, was, I don't want to exit, this guy. So let's first look at this code when it's working. So when I pass in a normal dictionary, in this case, actually this isn't going to work either, but whatever. No, this isn't going to work. Is it going to work? I have no idea if this is going to work or not. So what are we doing? So we've got some dictionary, and then we're going to call our example with some tensors and a dictionary. And what happens inside of this is we're going to assign a value to the dictionary in question, right? So basically there's some graph computation, and there's also some side effects. And the side effects are actually uncorrelated with the tensor computation. So ideally we just get a graph, but that's the entire thing. And then we also get some residual modifications to the tensor in question. So let's see what happens. So how come there's so many? Oh, I don't want to call it this many times. Okay, so the original bytecode is pretty simple, and the modified bytecode is a little more complicated, but we can see that a single graph got compiled, which in fact does have both of the operations. And then there's basically some code to update the global dictionary with the new data that was done. So this is what we want. Maybe this bytecode could be a little more optimized. Like the old bytecode was honestly better, but that's fine, right? So this looks pretty nice. Okay, so when I replace this with a collections order dict, this doesn't work. What happens? Uh-oh. Does this have my patch? Yes. So this sort of works. So what is working here is that we do have the compiled function, and we have a compiled function, we call it, and then we got something, and then so somehow Torch Dynamo doesn't know how to deal with this dictionary. So it graph breaks, right? So it decides, hey, I'm just going to go ahead and stop at this point and then run the dictionary update as is before, right? So this is one of the downsides of manually entering support for functions one by one, right? So whenever there's someone interacts with some object that we don't know about, we actually have to teach Torch Dynamo how to handle it in this case. And so order dict just happens to not be handled, even though dictionary is. There is something a little bit off though, which is, notice here, we do a multiplication between x and b, and it's directly inline in the bytecode here. So what that means is that we will never actually compile this part of the program because we didn't have those nice continuation functions, which were in separate frames so that we could actually turn Dynamo back on and start tracing in that case. So there's a bug here. We should have generated a continuation for this case. So what are we going to do? So let's try fixing this. So how are we going to go about fixing this? I've actually forgotten how to go about fixing this. So I kind of so one of the things, right, is like, why did this fail? Like, why did the dictionary call, like, was it not kosher? And if you remember from our presentation earlier, the way that this works, right, is we have a bunch of implementations for various things that are going on, and we have to, right? So we have to actually support the operation in question, in this dict thing. And if we don't, then when we fall through and we don't have support for the method in question, we'll call method on the parent class. But what that basically does is it just raises an error. It just says not implemented. So raising a not implemented error will ordinarily cause a graph break. So why does it not work for ordered dictionaries? Well, to answer this question, we have to look at when const variable actually gets constructed. All right, see you, CF Bulls. Thanks for coming. Yeah, this part's not important. It's just like applying. So I actually don't remember how this works. So let's look at the call construction sites for const variable. So when we build a map, right, this will result in creating a constant dict variable. There's a bunch of opcodes that create dictionaries. This is actually not the right code. Okay, I have no idea how to I have no idea where this code is because I actually fixed the bug in a different way when I was prepping. So let's just suppose that we have no idea how to do this in question. So there's still that other problem that I pointed out, which is that we didn't generate continuations, right? So let's go look at that code again. Right? So the way generic jump works is that when we when we see something that we don't know how to deal with, right, we create these call resume at things, and they will create the continuation frames for handling this sort of situation. So functions like this are not the only situation where we do graph break. For example, if we call a function that we don't understand, we will also break the graph in this situation. So we can see in this definition for call function, there's actually this nice decorator saying break graph if unsupported. And what does this do? Well, it goes ahead and it does the compilation, and then there's some stuff which we'll look at very shortly, and then this hopefully does the graph break. So let's go back to our example. And let's look at the original bytecode. And so the operation that's not supported is oh, this is the wrong example. Bug. I want bug. The operation that's not supported is a store subscript on a dictionary. So let's go ahead and look at that that method, and we see, hey, we attempt to pop, and we then try to call the setItem method. Okay, maybe I can answer that question that I had, which is how come this didn't work? So def call method, and then we're going to call setItem, and then no. So for some reason, oh, you know what's going on? It's because it's not a mutable local, but I'm not going to tell you about that. Okay, and then this is raise an exception, and there's none of that, like, you know, awesome break graph if unsupported, right? So the obvious thing to do is it's like, hey, okay, so if storing a subscript on a dictionary is not supported, then let's go ahead and break our graph. So let's see what this does. Oh no, index error pop from an empty list. Okay, so we should probably actually look at this function and see what it's actually doing. So what is this function doing? There's some graph state thing, and we save it, and then we run this function, and then if it raises an unsupported error, then we restore the graph state to the original state. Okay, so there's some snapshotting going on right here, right? So we're going to attempt to run the instruction, and that instruction may do modifications to the stack, but we don't want any of them, right? Because the instruction is about to fail, and if it fails, I don't want some sort of garbage intermediate state in that case. Then I'll go ahead and immediately compile the subgraph, and ooh, what's this comment? Note, assuming inst pushes 1. So what the heck? So after I compile my graph, I need to modify the state. So I'm going to like say, okay, run the opcode that I didn't support directly at this point, and I also need to modify the symbolic state stack to basically have the result, right? So what does this do? It basically says, well, remove. So stack effect, by the way, tells you how many entries on the stack an operation pops. So in this particular case, it's store subscript that pops 3 items, I think. And then there's a question which is, do we restore the graph state no matter what? The answer is no, because returning will just short circuit from the restore graph state call. So we need to pop 2 elements from the stack, but we're actually going to inst pushes 1. Something, and then we're going to push an unknown variable representing the output instruction in question. So why is this? So this assumes that the instruction pushes 1 argument, but if we look at the documentation for store subscript, well, actually, we don't need to look at the documentation. We can just look at this. We can see that this doesn't push anything, right? Storing a dictionary subscript doesn't actually storing a dictionary subscript doesn't actually push anything onto the stack. So if I just delete this, does that work? Hey, that did something. What did it do? So we can see that there are multiple graphs, and we can see that in the first graph we compile, we compile our function, we call it, and then we do the dictionary store subscript that we didn't support. There's actually a bunch of other stuff that I'm not sure why it's there. And then we go ahead and try to go to the resume continuation. Now, this is wrong, right? So now we're assuming inst pushes 0. So if I ever broke a graph on another function, that wouldn't work. But now all I need to do is just go ahead and add a parameter to this function to make it all work out. Okay, that's all the program content for today. But I'm going to hang out a bit, drink some water, answer questions, and then I will go teach my class. So thanks for everyone for joining me today, and see you next time. Oh, it actually didn't work. Its segmentation faulted. Lol. Thanks, Chili. Thanks for coming. Thanks, everyone, for showing up. It means a lot. All right. Well, it doesn't look like there are any questions, so I'm going to stop the stream for now. Folks coming to my class, see you in 50 minutes.